You break your arm, the whole diagnostic process is, well, it's wonderfully binary. You go to the hospital, they take an x-ray, and the doctor points to this jagged white line on a glowing screen and just says, there it is, that is the break.
Right. It's visible.
Exactly. It's categorized. The mechanics of the human skeleton are a known quantity. And honestly, it's kind of comforting because you can literally see exactly what is wrong with you.
Well, the mechanics of any physical system give you a definitive source of truth. You can look at the X-ray, or if we were talking about traditional on-premises servers, you can just walk into the cold aisle of the data center.
Yeah, you can hear the servers.
Right. You can see the amber light flashing on a failed drive bay, or you listen to the fan whining because the CPU is pegged at 100%.
Right.
There's this actual physical manifestation of the failure.
But when you step into the world of distributed cloud infrastructure, suddenly that X-ray machine is it's completely useless. The physical manifestations are just gone.
Yep, completely abstracted away.
Right. You are running applications with microservices that are scattered across virtual servers, distributed across multiple geographic regions. You have serverless databases firing off tens of thousands of concurrent queries a second.
And it's incredibly easy to provision all of this, right? With just a few lines of infrastructure as code.
It is, but the catch is, how do you actually know what is happening inside them? Like, how do you know if that architecture is actually healthy or if it is just silently bleeding out performance somewhere?
It is the definition of diagnostic muddy waters.
Yeah.
You cannot touch a cloud server. You need a completely different paradigm to see inside that environment. And so that is what we are digging into today for this deep dive.
We're getting into the actual mechanics.
Exactly. The mechanics of cloud observability, specifically within the Azure ecosystem. We are going to look at how to take this opaque distributed system and wire it up so that it tells you exactly what it is doing, why it is doing it, and when it's about to fail.
And just to set expectations for you listening, we are going to look under the hood today. No high-level, fluffy overviews, just the actual functional step-by-step mechanics of how you instrument applications using Azure Monitor, Application Insights, and log analytics workspaces.
Just the objective facts of how the systems connect.
Exactly. So let's unpack this from the very beginning. The core concept that everything else relies on here is telemetry. But what are we actually talking about when we say telemetry in a cloud context?
So telemetry is basically the raw data emitted by your cloud resources. Think of it like the exhaust coming out of an engine. But instead of carbon monoxide, it is pure operational information.
Okay, so every action generates some exhaust.
Right. Every time a virtual machine boots up, or every time a web application serves a page, or a database processes a query, it emits signals. Now, in the Azure Monitor ecosystem, that raw data primarily takes two distinct forms. We're talking about metrics and logs.
Let's break the mechanics of those down, because I see a lot of engineers conflating the two or just, using the term logs as a catch-all for literally everything. Why are they fundamentally different things?
Well, they serve completely different diagnostic purposes. And they're actually stored and processed differently under the hood. Let's start with metrics. Metrics are numerical, time series data.
So just numbers.
Just numbers. They're incredibly lightweight. You're basically capturing a value, a metric name, and a timestamp.
Like CPU percentage.
Exactly. For example, at 10:000 a.m., the CPU utilization on virtual machine A was 45%. At 10.0000 seconds, it was 47%. Because they're just numbers pinned to a timeline, they're cheap to store, and they are lightning fast to query.
Got it.
You use metrics for immediate performance tracking and for driving near real-time automated alerts.
So metrics are kind of like the vital signs, like the heart rate, the blood pressure. You don't need a medical degree to see that a heart rate of 200 means something is immediately terribly wrong.
That is a very solid way to visualize it. But, knowing the heart rate is high doesn't actually tell you why it is high.
Right, it just tells you that you have a problem.
Exactly. And that is where logs come in. Logs are the detailed medical history. They capture both structured and unstructured data, which offers rich context about specific events.
So what does a log look like compared to a metric?
Well, a log might tell you not just that a server crashed, but it'll give you this specific hex error code, the user ID that was executing the process at the time, the exact network port that dropped the connection, and maybe even the stack trace of the application code.
Which means they're fundamentally much heavier.
Oh, much heavier. You are capturing strings, JSON payloads, arrays. You do not use logs to trigger a sub-minute alert about CPU utilization. You use logs for deep forensic analysis and root cause troubleshooting.
Here's where it gets really interesting, though. We know we need this telemetry, right? These metrics and logs. But how is this data actually extracted from the resources? Does the Azure platform just like inherently know everything that's happening inside my architecture?
No, it doesn't. The instrumentation method entirely depends on the layer of the stack you are observing. The Azure platform only knows what it manages directly.
Okay, so native resources.
Right. For instance, native platform resources like an Azure SQL database or an Azure storage account, they use direct integration. They exist entirely within the Azure management plane, so they just emit platform metrics directly to Azure Monitor without you having to configure any agents.
Just out of the box.
Exactly. But when you deploy a virtual machine, Azure only sees the middle, or, well, the hypervisor layer, to be precise.
So it knows the VM is turned on.
Yes. It knows it has power. It knows how much virtual RAM is allocated, but it does not know what is happening inside the guest operating system.
So if I want memory utilization or Windows event logs or Linux syslog data, I have to bridge that gap somehow.
Yes, and you do that using agent-based auto-instrumentation. You deploy an extension directly onto the virtual machine's guest OS.
Okay.
That agent sits inside the operating system. It interfaces with the kernel, gathers those OS-level metrics and system logs, and then it securely ships them out to Azure Monitor. You do not have to write any code for this. You are just installing a localized daemon that basically acts as a telemetry courier.
Okay, so the agent is sitting on the VM, scooping up all the CPU and syslog data. But an agent is really just a collector, right? It has no real memory. If that VM dies, the agent dies with it, and the data on that local disk is just gone.
Poof, gone.
Right, so where is it actually offloading this data to keep it safe? Where is the permanent brain of this operation?
So that telemetry needs a centralized, durable storage layer. In Azure, that central repository is called the Log Analytics Workspace.
The Log Analytics Workspace.
Yes, this is the heart of Azure Monitor. It's a highly scalable multi-tenant data store. When you provision a Log Analytics Workspace, you are not just, creating a folder on a hard drive somewhere.
Yeah. Right, it's not just a file share.
Exactly. Under the hood, you are actually spinning up a dedicated Azure Data Explorer cluster. It organizes all this incoming telemetry into specific schema-defined tables, and that allows you to ingest and query massive volumes of data from literally thousands of different sources simultaneously.
Let's talk about the actual mechanics of provisioning that workspace, because our sources for this deep dive highlight a very specific real-world quirk that trips up a lot of engineers, especially if you are new to Azure. And I think it's a perfect example of how distributed systems actually function.
Oh, the UI delay quirk.
Yes. Let's say I run my infrastructure as code pipeline, or I just use the portal to create a new log analytics workspace. So
Right.
step one, I go to the portal, I pick my subscription, I create a resource group, I select East US for my region, and I hit create.
Right. Standard deployment.
The deployment says success, but immediately after, I go to configure another resource like an app service, and I try to link it to my brand new workspace. But the drop-down menu is just empty, the workspace is completely invisible.
Yeah, I've seen engineers tear their hair out over this. This is a classic lesson in the eventual consistency of cloud control planes.
So what's actually happening there?
Well, when you instruct Azure to create that workspace, your command goes to the Azure Resource Manager, or ARM. ARM says, okay, the configuration is valid. I have initiated the deployment.
And it tells you it succeeded.
Right. The deployment reports as successful because ARM successfully handed the job off to the backend storage clusters. But it takes time for that new resource's metadata like its location, its ID, its routing information to actually propagate across all the various regional DNS and management endpoints globally.
So my browser is querying a regional endpoint that literally hasn't received the memo yet.
Exactly. The workspace physically exists on a server somewhere, but the global directory hasn't fully synchronized. So if a newly provisioned resource does not immediately appear in an integration menu, do not assume your deployment failed or that you corrupted your Terraform state.
Just take a breath.
Yes, just wait a few minutes, let the control plane synchronization complete, and then just refresh the interface.
Okay, so we waited a few minutes. Our workspace is provisioned. The central repository is ready. Let's connect the agents. We talked about virtual machines using agents to bridge the gap between the guest OS and Azure. But there is a pretty massive architectural shift happening right now regarding how those agents operate.
Yes, it's a critical transition. Microsoft is deprecating the legacy Microsoft monitoring agent, the MMA. The modern standard moving forward is the Azure Monitor Agent, or AMA.
AMA.
Right. And the difference between them isn't just, a version number update. It is a fundamental shift in how telemetry is filtered at the edge.
Let's unpack that. Why was the legacy MMA agent a problem?
Well, the legacy MMA was essentially a vacuum cleaner. It was notorious for overcollecting. You would install it, point it at a log analytics workspace, and tell it to grab Windows event logs.
And it would grab all of them.
It would frequently grab everything, or at least it operated with very blunt filtering. When you are paying for log ingestion by the gigabyte, vacuuming up every single informational system event across, say, 500 virtual machines, that is incredibly expensive.
Yeah, I have actually heard war stories about this. An engineering team spun up a new cluster, turned on the legacy agent, and someone accidentally left a verbose debug flag active on the local machines. The agent just dutifully collected millions of debug logs and blew through the entire department's monthly cloud budget in like 3 days.
Yeah, that is painfully common. And that is exactly the scenario the new architecture solves. The Azure Monitor agent introduces a concept called data collection rules, or DCRs.
DCRs. So what is a DCR mechanically?
A DCR is a completely separate Azure resource. It is essentially a JSON-formatted policy document that explicitly dictates exactly what telemetry the agent is allowed to pull and where it should send it.
So the filtering happens locally on the virtual machine itself before the data ever hits the network.
Precisely. You define a DCR that says, only collect Windows event logs classified as critical or error. Ignore all informational events.
Okay.
And only collect CPU metrics every 60 seconds.
And then you attach that rule to the VM.
Right. You bind that specific DCR to a group of virtual machines. The AMA agent downloads that rule, parses it, and then it only transmits the data that matches the criteria. It provides surgical control over your telemetry at the edge, which drastically reduces unnecessary data ingestion costs.
Okay, I want to push back on the network transit piece for a second. Let's say I am running a highly sensitive, regulated database on a virtual machine. I have my data collection rule set up perfectly to only grab critical security logs. But I absolutely do not want my private, unencrypted server logs traversing the public internet to reach the log analytics workspace.
Sure.
Because in a default setup, Azure Monitor endpoints are public, right? So am I just out of luck here?
Not at all. In enterprise architectures, telemetry traversing the public internet is often a non-starter for compliance reasons. You just can't do it. To solve this, you implement an Azure Monitor private link scope, or AMPLS.
AMPLS. Okay, this is a brilliant piece of network engineering. How does it work under the hood? Does it just create a VPN tunnel?
It is actually more elegant than a VPN. It relies on DNS hijacking within your own virtual network.
DNS hijacking?
Yes. When you configure an AMPLS, you create private endpoints. These are basically virtual network interfaces with private IP addresses that sit inside your own Azure VNet. You then link your Azure Monitor resources, like your log analytics workspace, to this scope.
So my local VM thinks it's talking to the public internet, but it's not.
Right. You update your internal Azure DNS private zones.
Mm.
Now, when the Azure Monitor agent on your VM tries to resolve the URL for the log analytics ingestion endpoint, the internal DNS intercepts that request.
Oh, wow.
Yeah. Instead of returning Microsoft's public IP address, it returns the private IP address of the endpoint sitting inside your VNet. So the telemetry data flows from the VM to that private endpoint, and then it rides the internal Microsoft Azure backbone network directly to the workspace.
So it never touches the public internet?
Never.
Yeah.
It completely shields your transit from external interception.
That is a phenomenal piece of architecture. So at this point, we have our infrastructure securely reporting in, we have CPU metrics flowing, we have critical OS event logs routing over private network links directly into the workspace.
The underlying metal is healthy.
Exactly. But there is a massive blind spot here. Getting server logs is great, but it does not tell us a single thing about our compiled application code.
Not a thing.
Right. If a user clicks a submit order button on my website and the screen just hangs for 30 seconds, the server CPU might look totally fine. The infrastructure is green, but the business application is fundamentally broken. The OS agent cannot read the mind of a Python script.
And this is where we shift from the macro-level observation of infrastructure down to the micro-level execution of your code. To look inside the application, you need an application performance management service. In Azure, that is Application Insights.
Application Insights. Now, the sources mentioned that Application Insights is linked to the log analytics workspace. But how does that architecture actually piece together? If the workspace is the database, what exactly is App Insights?
Think of Application Insights as a highly specialized intelligence layer and user interface designed explicitly for developers.
Hmm.
It understands code, it understands web requests, but you are absolutely right. It does not store the data itself anymore.
Oh, it used to.
It used to have its own storage backend, but Microsoft unified it. Now, when you provision an Application Insights resource, a mandatory configuration step is linking it to your log analytics workspace. By doing this, you're instructing App Insights to take all the application telemetry it gathers and write it directly into the backend tables of the workspace.
So the workspace remains our single source of truth. We aren't creating a siloed data store just for the dev team.
Exactly.
But how does the application actually talk to this intelligence layer? The OS agent is just a daemon running in the background. My application code is isolated, so how do I bridge that?
This requires manual instrumentation using application-specific software development kits, or SDKs.
Hmm.
You, as the developer, actually implement the Application Insights SDK directly into your code base.
Step by step, how do I do that?
Well, for .NET application, it is a NuGet package. For Python, it's a pip install. You add the library to your project, and then you provide it with a connection string.
And where does that connection string live? Do I hard code it?
No, never hard code it. It usually sits in your environment variables or your configuration files, like the appsettings.json file in a .NET app. When you created the App Insights resource in the Azure portal, it generated a unique connection string for you. It contains the ingestion endpoint URL and a specific instrumentation key. When your application boots up, the embedded SDK reads that string, authenticates with the Azure endpoint, and opens a telemetry pipeline.
Okay, the pipeline is open. The SDK is sitting inside my compiled code. What kind of telemetry am I getting out of the box without having to write 100 lines of custom logging code myself?
The default auto-collection capabilities of the SDK are remarkably deep. Just by including the SDK in the connection string, it hooks into the underlying frameworks of your application to intercept several vital streams.
What's the first stream?
First, it tracks all incoming HTTP requests. It monitors the web server pipeline, logging every single incoming request. It records the URL path accessed, the HTTP verb like GET or POST-T, the status code returned, and crucially, exactly how many milliseconds it took your application code to generate that response.
So I instantly know if my checkout page is taking 5 seconds to load, whereas the home page takes 200 milliseconds.
Yes, you instantly see throughput and latency bottlenecks. Second, it automatically tracks exceptions.
Oh, that's huge.
It is. The SDK hooks into the global exception handlers of your runtime environment. If your code throws an unhandled exception, say a null reference error, the SDK catches it before the application crashes completely.
And what does it capture?
It captures the full stack trace, showing the exact class, the method, and the line of code that triggered the failure. It takes a massive amount of detective work out of bug hunting.
That is fantastic. But there is another default metric here that I think is the most valuable feature of the entire suite: dependency tracking. Explain how the SDK handles dependencies.
A modern application rarely executes its logic in a vacuum. It relies on external components. To render a page, it makes a query to a backend SQL database, or it calls an external payment gateway API over HTTP, or it reads a blob file from a storage account.
Right.
These outbound calls are called dependencies. The Application Insights SDK automatically instruments the HTTP clients and database drivers within your application to track these outbound calls.
So it knows what my code is talking to.
It knows what it is talking to. It knows the specific SQL query text it sent. It knows the target URL of the external API, whether the call succeeded, and exactly how long the external dependency took to respond.
See, this is why I think it's the most valuable feature. App Insights essentially acts as an objective referee between your development teams and your infrastructure teams.
Oh, absolutely.
Because if a user complains the application is slow, the immediate reaction is almost always a cross-team blame game. The front-end team blames the database administrators look at the server CPU and say, no, the database is fine, blame the front-end code.
Right, the endless ping-pong of IT support.
Exactly. But dependency tracking mathematically proves where the bottleneck is. It can definitively say the total request took 5 seconds, but the front-end code only took 50 milliseconds. We spent 4.95 seconds waiting on this exact SQL query to return data. End of argument.
It completely isolates the fault domain. And we can take that concept of tracing a step further into highly distributed architectures with distributed tracing.
Right, because an application isn't always just a front end and a single database. What if I have a microservices architecture? Like, a user clicks buy, The request hits an API gateway, which calls an inventory service, which drops a message on an Azure Service Bus queue, which is picked up by a backend worker, which finally updates a database.
That's a lot of hops.
It is. So how on earth do you trace a single user's action across 5 different independent servers?
The mechanics of distributed tracing rely on injecting and propagating correlation IDs.
Okay, how does that start?
When that initial HTTP request hits your API gateway, which is the very first node in your architecture that has the App Insights SDK installed, the SDK generates a unique, globally distinct identifier. It often follows the W3C trace context standard.
Got it.
It takes this ID and actively mutates the outbound HTTP headers, inserting a header like trace parent.
So it stamps the request?
It stamps the payload. When the API gateway makes an HTTP call to the inventory service, that trace parent header goes with it. The SDK running inside the inventory service intercepts the incoming request, sees the header, and says, I am part of an existing transaction.
So it doesn't create a new master ID?
Exactly. It logs its own internal execution time, creates a new span ID for its specific piece of work, but it tags it all with that overarching correlation ID. It then passes the baton to the service bus, and so on down the line.
So when all these different services independently flush their telemetry back to the Log Analytics workspace, they are all tagged with the same master ID.
Yes, and because they all live in the same unified workspace tables, Application Insights can simply query the database for that single correlation ID and reconstruct the entire transaction flow end to end.
Wow.
It builds a visual application map of the distributed request. You can visually see exactly which hop in the microservice chain caused the failure or the slowdown.
Okay, but what if I want to track something that isn't a default HTTP request or a standard dependency? What if I have specific business logic? Say I am running an e-commerce site, and I want to know every time a user clicks the empty cart button. The SDK doesn't natively know what that button means to my business.
For that, developers utilize the custom telemetry capabilities of the SDK. You write a few lines of code to explicitly send data to App Insights.
Like custom events.
Yes, you can use a method like trackEvent, empty cart clicked. Now, every time that function executes in your code, a discrete event is logged, and you can attach custom properties to that event, like the user's region or their account tier.
What about custom numbers, like the value of the cart?
You can use the trackMetric method for that. It records arbitrary numerical data calculated by your business logic, like the total monetary value of the items that were just deleted from the cart. So you're blending operational data with business data.
Okay, let's take a breath and look at the absolute mountain of data we have just generated.
It is a lot.
It's massive. We have agents pushing OS metrics and syslogs. We have Application Insights SDKs generating HTTP request telemetry, exception stack traces, dependency durations, and custom business events. We are ingesting potentially millions of discrete records an hour into the Log Analytics workspace. But data without analysis is just expensive noise.
Right.
How does a human operator actually interact with this massive schema-structured data store to find the one error causing an outage?
You interrogate the workspace using the Kusto query language, or KQL.
KQL.
Yes, this is the native querying language of Azure Data Explorer and Log Analytics. Inside the workspace, all that incoming telemetry is routed into specific tables. Your virtual machine CPU data lands in a table named perf. Your application exceptions go to a table named exceptions. Your custom business events go to custom events. KQL is the tool you use to slice through those tables.
I know a lot of engineers who are masters of SQL, and when they look at KQL, the syntax feels completely backwards. Why didn't Microsoft just use standard SQL for this?
SQL is fantastic for relational databases, but KQL is explicitly designed for read-only, high-performance parsing of massive time series datasets and unstructured text logs.
Okay, so it's optimized for logs.
Highly optimized. The syntax is built around a sequential pipeline model, which is fundamentally different from SQL's declarative model. In KQL, you process data step by step, using a pipe character to pass the output of one operation directly into the input of the next.
Give me a practical example. Let's say I want to find the top 5 URLs on my application that are generating the most 500 internal server errors over the last 24 hours. Step by step, how does that KQL pipeline actually flow?
Okay, you start by defining the source. You literally just type the table name, requests.
Just requests.
Yep. Then you use a pipe character. The very next operation should almost always be a time filter, because filtering by time prunes the dataset and drastically speeds up the query. So you pipe into a where clause. Where timestamp it go?
24.
Okay, now I have all requests from the last day.
Next pipe. You filter for errors, where success equals false in result code equals 500. Okay, now I only have the server errors.
Right. Next pipe, you summarize the data. The summarize operator in KQL is incredibly powerful. You write, summarize error count by URL.
So that groups them.
It aggregates the remaining logs, grouping them by the URL path and counting the occurrences. Finally, you pipe one last time to order the results. Top 5 by error count.
So it's requests, time filter, error filter, summarize top 5. It reads exactly how your brain thinks about filtering data.
Exactly. It is a logical flow. And because it utilizes schema-on-read capabilities, you can actually parse JSON payloads or extract custom strings out of raw log text directly within the pipeline using operators like parse or extract without having to predefine those columns in a database schema.
That is incredibly powerful for an engineer actively sitting at a keyboard during an incident. But, I do not want to pay engineers to sit there running KQL queries all day, manually refreshing dashboards just in case something breaks.
No, you go crazy.
Right. The system needs to watch itself.
Yeah.
So how do we configure Azure Monitor to automate this analysis?
We move from manual observation to automated alerting. You configure Azure Monitor alerts, which consists of 2 main components. You have the alert rule, which is the logic that detects a problem, and the action group, which is what the system does about it.
Let's look at the rules first.
Okay, the most common are metric alerts.
The vital signs.
Right. Metric alerts evaluate those lightweight time series data points at a very high frequency, often every minute. You define a static threshold. Like if the average CPU utilization of virtual machine A exceeds 85% for a continuous 5-minute window, trigger.
Simple enough.
Because metrics are so small, these alerts are highly responsive and computationally cheap for the platform to evaluate. They are stateful, meaning the alert fires when the condition is met, and it automatically resolves itself when the CPU drops back down below 85%.
But what if I want to alert on something more complex than just a simple number? What if I want an alert if my e-commerce application logs more than 50 empty cart clicked custom events in an hour? That data is sitting in a log table, not a metric.
For that, you configure a log search alert. This is where you weaponize KQL. You take a KQL query-like one that counts custom events or searches for a specific exception stack trace, and you wrap it in an alert rule.
Oh, I see.
You tell Azure Monitor, run this specific KQL query against the workspace every 5 minutes. If the number of results returned by the query is greater than 50, fire the alert.
So the platform is basically just running my query on a cron job behind the scenes.
Essentially, yes.
Yeah.
And there is a third critical type, activity log alerts. While metrics and logs monitor the performance of your resources, the Azure activity log tracks the control plane operations of the Azure subscription itself. It monitors the who did what to which resource events.
Give me a scenario where I need an activity log alert.
Imagine you have a highly secure network architecture with a network security group that strictly blocks inbound traffic from the public internet. You configure an activity log alert to trigger any time an administrator modifies that specific network security group rule.
Right, because that's a security risk.
Yes. If someone accidentally opens port 3389 to the world, the activity log alert detects that architectural configuration change instantly, regardless of the actual server performance.
Okay, so the condition is met, the CPU spikes, or the KQL query finds the errors, or the firewall rule is changed, the alert rule triggers. But what actually happens? An alert firing in a vacuum doesn't solve the problem.
The response logic is contained entirely within an action group. When you define an alert rule, you attach an action group to it. It is an independent resource that holds a collection of notification preferences and automated actions.
Break down the mechanics of those actions. What can an action group actually execute?
At the most basic level, it handles routing notifications. It can send an email to the dev team, dispatch an SMS text message to the on-call engineer, or trigger a push notification to the Azure mobile app.
Just paging people.
Right. But the real power lies in system integration and automated remediation. An action group can trigger a webhook.
And a webhook is just an HTTP payload, right?
Yes. When the alert fires, Azure packages all the context, the resource name, the metric value, the timestamp into a JSON payload and pastes it to an external URL.
What can I do with that?
You can use webhooks to post the alert directly into a dedicated Slack channel or a Microsoft Teams channel, giving the engineering team immediate visibility in their collaboration tools. Furthermore, you can use secure webhooks to integrate directly with IT service management tools like ServiceNow, automatically opening, populating, and assigning an incident ticket without a human ever touching a keyboard.
Can the action group actually fix the problem itself? Let's say a background worker process crashes. I don't want to wake up at 2:00 a.m. to restart a service.
It absolutely can. Action groups can trigger Azure Logic Apps, Azure Functions, or Azure Automation Runbooks. This allows you to write custom code or graphical workflows that execute in response to the alert.
Give me an example.
If a virtual machine's memory utilization hits 95%, the action group can trigger an Azure function script that automatically reaches into the virtual machine, restarts the memory leaking service, and logs the remediation action. It turns your observability stack into a self-healing system.
The sources also highlight a feature inside Application Insights called Smart Detection. This seems entirely different from setting up static KQL queries or threshold limits. How does this work?
Smart detection is a fundamental shift from static rule-based alerting to machine learning-driven baselining. When you connect Application Insights, it begins analyzing your application's telemetry over time to establish a dynamic baseline of normal behavior.
Normal behavior.
Right. It learns that your application typically has a 1% failure rate, and the database queries usually take 150 milliseconds.
So it learns the rhythm of the application.
It learns the rhythm. If you deploy a new version of your code, and suddenly the failure rate jumps to 5%, or the database latency creeps up to 800 milliseconds, the machine learning algorithm automatically detects that the current telemetry deviates significantly from the historical baseline.
Even if I didn't set a rule for 800 milliseconds.
Exactly. It generates an anomaly alert proactively without you ever having to manually configure a threshold rule that says, alert if failure rate is greater than 5%. It finds the unknown unknowns.
We have covered an immense amount of architectural ground today. The underlying telemetry agents, the centralized workspace clusters, the SDK intelligence layers, the KQL pipelines, and the automated self-healing action groups. To bring this all together, the sources evaluate these configurations against the Azure Well-Architected Framework.
The Well-Architected Framework, or WOEF, is a set of guiding tenets provided by Microsoft to improve the quality of a workload. It asks you to evaluate your architecture across 5 pillars: reliability, security, cost optimization, operational excellence, and performance efficiency.
And where does observability fit?
The observability stack we've built today maps directly to the operational excellence pillar.
Let's apply that lens to a practical scenario. Imagine a basic web app architecture. We have an Azure App Service hosting the front end, talking to an Azure SQL database on the back end. It was spun up quickly by a small team. They left the default monitoring on, but they didn't implement any of the tools we discussed today. No log analytics workspace, no App Insights SDK, no alerts. How does that architecture hold up under the well-architected framework?
From the perspective of operational excellence, that architecture
Fails completely.
It might function perfectly well from a compute standpoint, but operationally, it is entirely reactive. The team has no structured observability strategy. If the SQL database starts slowing down because of a missing index, the team will only know there is a problem when a frustrated user calls the help desk to complain that the app is timing out.
Right?
They have to scramble, manually parse isolated server logs, and guess at the root cause. They are flying blind.
So how do we elevate that architecture to meet production-grade standards?
You implement the stack. You provision a centralized log analytics workspace to serve as the unified brain. You deploy the Application Insights SDK into the web application code to capture the HTTP requests, and crucially, the dependency calls to that SQL database.
Get the pipeline flowing.
Yes. You configure the app service and the SQL database to stream their platform diagnostics natively to the workspace. And finally, you author KQL-based log alerts and metric alerts tied to action groups to notify the engineering team the moment database latency exceeds your acceptable threshold.
The defining characteristic of operational excellence is moving from reactive troubleshooting to proactive observability. You know the system is degrading before the user ever notices.
That is the ultimate goal.
Let's summarize the mechanical journey we took today. We started by defining the fundamental difference between lightweight metrics and heavy contextual logs. We looked under the hood of the log analytics workspace, understanding it as a dedicated data exploration cluster subject to the eventual consistency of the Azure control plane.
We covered a lot of ground.
We did. We explored how the new Azure Monitor agent utilizes data collection rules to surgically filter telemetry at the edge, and how private link scopes use DNS hijacking to secure that data transit over the internal backbone.
We then moved up the stack to the compiled code, detailing how the Application Insights SDK intercepts the runtime pipeline to generate HTTP and exception telemetry.
The dependencies.
Right, we highlighted how dependency tracking injects correlation IDs into request headers to construct distributed traces across microservices. And we finished by turning that raw data into actionable intelligence using the KQL sequential pipeline, closing the loop with automated alerts and action groups capable of self-healing workloads.
The takeaway for you, the listener, is recognizing that observability is not a checkbox. It is not something you turn on with one click. It is a layered, deliberately engineered architecture that starts with the foundational storage workspace and builds upward to the intelligence layer of the application SDKs.
And as we wrap up, I want to leave you with a final philosophical shift regarding how you manage this architecture. As your distributed systems scale, as you add hundreds of microservices, attempting to log every single piece of telemetry becomes mathematically and financially untenable.
It's just too much data.
Storage is not free, and querying petabytes of verbose informational noise drastically slows down your KQL analysis during a critical outage.
You cannot just hoard the data.
You cannot. The next evolution in mastering cloud observability isn't learning how to log everything. It is learning how to strategically define what specific telemetry is actually valuable enough to retain. It is about understanding your business requirements well enough to configure granular data collection rules and intelligent workspace retention policies that perfectly balance your need for deep operational visibility against the hard realities of storage efficiency and cost optimization.
Returning to our X-ray metaphor from the beginning, if you break your arm, the doctor only takes a picture of your arm. They do not run a full-body MRI just in case you might have a bruised rib. They know where to look. They capture only the images that are actually necessary to diagnose a specific problem, and they use that targeted information to heal the patient. That is how you build true, efficient observability.
Gather what matters, automate the response, and leave the noise behind.